I shall define the compressibility of fluid. Compressibility of any substance is the measure of its change in volume under the action of external forces, usually the compressive forces. The degree of compressibility of a substance is characterized by the bulk modulus of elasticity. How do we define bulk modulus? Bulk modulus of elasticity, K, we define as volumetric stress by volumetric strain, where delta V and delta P are changes in the volume and the pressure respectively, and V is the initial volume. Negative sign only means that as the volume decreases, the pressure will be increasing. For a given mass of substance, the change in volume and density rho satisfies the relation delta V by V, change in volume by initial volume, is minus delta rho by rho. Therefore, bulk modulus K can also be defined as rho into dP by d rho, where P is the pressure and rho is the density. The values of K are very high for liquids as compared with those of gases. Therefore, hence liquids are treated as, are termed as incompressible fluids, and gases are known as compressible fluids. This is a very important distinguishing between the gases and liquids. For example, K of water is 2 into 10 power 6 kilonewton per meter square, bulk modulus of water, whereas K of air is 101 kilopascal at atmospheric pressure. So look at the difference between the K values of water and air. So I can say air is about 20,000 times more compressible than water. Therefore, water can definitely be treated as incompressible fluids. Now, compressibility K compressibility C. Compressibility C of fluid is 1 by bulk modulus of elasticity. Therefore, C is 1 by K. So I can define C as 1 by rho d rho by dP, or minus 1 by V delta V by delta P. For any gaseous substance, usually a change in pressure is associated with a change in volume and in change in temperature. For gases, particularly for ideal gases, we can write thermodynamic equation of state as we know that P is rho or T. The change in pressure is associated with change in density and as well as change in temperature, where R is the gas constant. We already know this is a thermodynamic relation. Thermodynamically, PV is equal to MRT. This is the same equation as that of PV is equal to MRT, or ideal gas equation or perfect gas equation. So I want to highlight here that for liquids, density is practically a constant, whereas for gases, density is a function of pressure. Therefore, liquids are termed as incompressible fluids. So now onwards, whenever densities are treated as constant, that means the fluid is treated as incompressible fluid. If density is a function of pressure, it means the fluid should be compressible. Usually it is gases. All the liquids are incompressible fluids. But there is one important note here that under very small changes of density conditions, that is if the density changes are less than 5%, even the gas flows can be treated as incompressible flows, because such density changes less than 5% can always be neglected, and practically that particular gas flow can be treated as incompressible flow if the density changes are less than 5%. So I can say that if the velocities of flow in the case of gases are in such a fashion that the density changes of gases are less than 5%, then such flows can be treated as incompressible flows. So now here I use a very important number known as Mach number for distinguishing between compressibility and incompressibility of a fluid. Mach number is defined as square root of inertia force divided by elastic force. Mach number m is also defined as velocity of fluid divided by velocity of sound in fluid at local conditions. The velocity of sound or sonic velocity A is defined as square root of bulk modulus divided by density of the fluid. It can also be written as square root of dou P by dou rho at isoentropy conditions. If Mach number is greater than 1 implies flow is supersonic. If Mach number is less than 1, it means flow is subsonic flow. If m is equal to 1 implies flow is sonic flow. So for flows of fluids, flow is termed as incompressible if Mach number of flow is less than 0.3. That is roughly the velocity of flow is about 110 meters per second. For example, if the air flow is around 110 meters per second, the flows of air can be treated as incompressible flow. Example I can give. The velocity of flow of air up to 110 meters per second under local standard conditions, then flow is treated as incompressible flow because density changes are not appreciable. The density changes are maximum 5% only. So this is very important, distinguishing between compressibility and incompressibility of a fluid. All liquid flows are incompressible flows. Since density is constant. If rho is a function of pressure and if the density changes are appreciable, and if density changes are more than 5%, implies flow is compressible flow. Compressible flow is an analysis of compressible flow is slightly advanced fluid mechanics. Now I shall solve problems on fluid properties. First problem. The problem is given like this. A body weighing 441.45 newtons with a flat surface area of 0.093 meter square slides down lubricated inclined plane, making a 30-degree angle with the horizontal. For viscosity of 0.1 Newton second per meter square and body speed of 3 meters per second, determine lubrication film thickness. The solution to this problem is given like this. It's an inclined plane over which the flat plate having a contact area of 0.093 meter square is sliding over a lubricant film of thickness Y. Thickness of the lubricant is Y. The plate is sliding down with a velocity of 3 meters per second. Since the gap between plate and inclined plane which is filled with the lubricant is very small, that is Y is very small, dV by dy can be taken as V by Y, that is velocity variation with respect to Y is treated as linear. That is, if this is a plate, if this is inclined plane of 30 degrees, the velocity variation can be treated like this. If this is the plate, the velocity variation can be treated as linear. Therefore, from Newton's law of viscosity, tau is equal to mu into dV by dy, that is mu into V by Y. What is tau? F by A is equal to mu into V by Y, implies what is the force that is acting on the plate going downwards? That is weight into sin 30 divided by area is equal to mu into V by Y. What is weight? 441.45 into sin 30. What is the area of contact? The weight component that is acting is W sin 30, which is opposed with the viscous resistance. This is viscous resistance, viscous force. Viscous force is a non-conservative force. So the downward weight component is exactly balanced upwards with the viscous force or viscous resistance offered by lubricant film thickness. That is the reason why net force along the plane acting on the plate is 0. The body is sliding down with constant velocity. So the weight component is nothing but the viscous force upwards acting on the plate. F divided by area is 0.093 meter square. This is given by Newton by meter square is equal to mu is given as 0.1 into what is the velocity? It is sliding 3 meters. Y is unknown. Therefore, Y is obtained in meters. The answer for Y should be obtained as 0.126 millimeters. So as we have assumed the gap is very small, the assumption is right. So for such a small gaps, narrow gaps, the velocity profile can be assumed as linear, and hence dv by dy can be treated as v by y. The velocity gradient can be treated as v by y. Hence the problem. Problem number 2. It is on the surface tension. If the pressure inside a droplet of water is 196.2 Newton per meter square in excess of the external pressure, what is the diameter of droplet? Given that sigma of water in contact with air at 20 degrees centigrade is 0.07358 Newton per meter. The solution to this problem is given as, this is the water droplet having the radius r. The pressure P gauge inside water droplet, that is pressure in excess of the droplet above atmosphere, outside is atmosphere. The P gauge is the pressure inside the droplet in excess of the outside atmospheric pressure is given by 2 sigma by r, 2 into 0.07358 divided by radius. P gauge is given as 196.2 Newton per meter square, implies R is obtained in meters. Diameter is 2 into R. The answer should be 1.5 millimeter. That is the diameter of the water droplet. Next problem, what I consider is a cylinder of 0.1 meter diameter rotates in an annular sleeve 0.102 meter internal diameter, at 100 rpm. The cylinder is 0.2 meters long. If the dynamic viscosity of lubricant between the two cylinders is 1 poise, find the torque needed to drive the cylinder against viscous resistance. Assume that Newton's law of viscosity is valid and viscosity profile is linear, and velocity profile is linear. The solution to this problem could be given like this. First of all, let me draw a figure depicting the problem. This is the shaft rotating in a sleeve. This is the sleeve. This is the axis of the cylinder. It is rotating with a certain RPM, that is 100 RPM. The diameter of the cylinder is 0.1 meters, whereas the internal diameter of the sleeve, this is 0.102 meter. So the gap between these, this is all lubricant. The gap, this is lubricant having the viscosity of 1 poise. The sleeve is fixed, the cylinder is rotating with a RPM of 100. Naturally, as the cylinder is rotating inside the sleeve, what is the tangential velocity of the cylinder? Same is the velocity of the fluid layer that is attached itself to the cylinder. A certain layer of the fluid is attaching itself to the cylinder. It cannot slip from the cylinder. Therefore, whatever the tangential velocity of the cylinder at its periphery, same is the velocity of the fluid layer. Therefore, first of all, I calculate that the velocity of fluid layer attached or sticked or gets adhered to the cylinder. Stick to cylinder is V is equal to R into omega, where omega is the angular velocity of the cylinder. The torque exerted is equal to force into radius. What is force? Viscous stress into area into radius. What is stress? Mu into dV by dy from Newton's law of viscosity. What is the area of contact? Pi d into L into radius. Since velocity profile is linear, dV by dy is V by y. Therefore, torque is equal to mu into V by y into pi into diameter is 2 into radius of the cylinder, where L is the length given as, what is the length given? 0.2 meters into R, from which substituting all the values, the torque value could be obtained. Please maintain the mu is given as, what is the mu value? 1 poise. So, what is the mu? 1 by 10 Pascal second. So, please substitute mu as 1 by 10. Velocity is obtained as R into Omega is 2 pi n by 60, that is the velocity. The y gap, what is the y? This is the gap y. Please indicate that y here. What is y? 0.102 minus 0.1 divided by 2. That is the value of y. I have indicated in the figure. This is y. Y is known, velocity is known, radius of the cylinder is known, length of the cylinder is 0.2 meters. Substitute all the values. We would obtain the torque as 0.1645 Newton meter. Please substitute mu as 1 by 10 Pascal second, because mu is given as 1 poise. 1 poise means 1 by 10 Pascal second. Velocity is r omega. So all the values are known. Torque could be calculated. Hence the problem.